This video is meant to be a bit of an introduction to exponential functions in general. We're going to talk about the generic exponential function and then look at a couple of graphs just to see what type of things you can expect from an exponential function. Obviously each one's a little different, but there are some things we can sort of generalize. So to begin with, we've got the generic exponential function f of x equals a times b to the x power. It is important that you understand simply having an exponent does not mean that you have an exponential equation or an exponential function. When we refer to something as an exponential function, what we're saying is the input, the x value, is in the exponent. Right? I mean, if you talk about like a quadratic is x squared, right? It has an exponent of 2, but that doesn't make it exponential. It's a quadratic. We've already talked about that. Same with the cubic, right? Or something like that. It's not simply having an exponent, it's when the variable, when your input, when the x is in the exponent, that's when you have an exponential. There are a few constraints to exponential functions, few definitions for the few rules for them. We see them written here. A is not allowed to be 0. That kind of makes sense because a is being multiplied to the rest of the problem, and so if a is being multiplied to everything in the equation and it's 0, well, we know 0 times anything is just 0, so that would be kind of a pointless graph, right? It'd just be a flat line, wouldn't be exponential at all. B needs to be greater than 0. That's just simply saying that b is your base, it's what the exponent is going to, and so if b is not greater than 0, then that would mean it's negative, right? And plugging a negative in for a base would kind of be a problem, because when you take a negative number to an odd exponent, we get a negative answer. But when we take a negative number to an even exponent, we get a positive answer, right? For example, negative 2 squared is positive 4, but negative 2 to the third is negative 8. And so if you have a b value that's negative, your graph's going to be jumping all over the place between, being above the x-axis and below the x-axis, and it'd be completely useless to us. Lastly, b is not allowed to equal 1. And that's simply because, again, b is the base that you're taking to the power of x, and so the point of an exponential is when I'm plugging in, point of any function really is when I'm plugging in an x value, I should be getting different y values each time, right? And so whenever you're plugging in when you take 1 to any power, it's just 1, right? So that doesn't really help you because then it doesn't matter what x value you plug in, you're always getting 1. So again, you'd have a flat line, and again, that's not exponential. Let's take a look at a reasonably simple exponential function, pretty much as simple as we could really give you. F of x equals 2 to the x power. So that's about the lowest integer base that I could give you because we already said that b can't be 1. And notice that I am not giving you an a value to contend with. Right? Technically, if you wanted to give an a value, then how you'd really want to look at this instead would be 1 times 2 to the x power is what we're technically doing here as a function if you want to think of it as having an a and b term. But it really doesn't matter which way you look at it, right? It's the same either way. So anytime that we're graphing a function for the first time, we should be using an xy table. Right? Xy tables can be used to graph any function that you could possibly be asked to do. And the beauty of XY tables is we can pick any x value we want, plug it in, and just see what we get for an answer. And it's a good way to start figuring out some things about a function that we may not be familiar with. I'm going to start by plugging in 0 for x, because that's usually a reasonably good place to start. And if nothing else, it will tell us our y-intercept, which is usually a point of interest on any graph. So if we plug in 0, then that would mean we are effectively taking 2 to the 0 power. Well, if you remember your properties of exponents, anything taken to the 0 power is going to equal 1, guaranteed. So 0, 1 would be a coordinate point for this graph. Put a dot there. I would point out that really your a value is what's going to determine your y-intercept, because again, anything to the 0 power is 1. So every time you plug in 0 for x, you're going to end up getting 1 out of that. So it really just depends on what you're multiplying by. Here, we were multiplying by 1, and so that's not changing anything. If our a value had been 3, well, then our y-intercept would have been at 3, right? So whatever your a value is pretty much going to determine what your y-intercept is going to be. Excluding any shifts or transformations, obviously you can always add more things on to make something do what you want it to. So that's still just kind of somewhat of a generic showing. Let's do some positive numbers. Let's say we plugged in positive 1 for x. Well, that'd be 2 to the first power. 2 to the first power is 2. So 1, 2 is a coordinate point. Now I certainly wouldn't want to stop there. Obviously we need to plug in more. You can never graph a function just by plugging 2 points in unless you already know that it's linear. Because if you only graph 2 points, then every time you connect 2 points, it's always going to give you a straight line. So unless you're positive it's supposed to be a straight line, you need to plug more points in. Might as well do another positive one. I like to do at least 2 positive and 2 negative. If we plug in positive 2, 2 to the second power, or 2 squared, would be 4. So now we see that it's a good thing we didn't just connect those 2 dots, because that's certainly not going to be a straight line, right? It's curving. If you wanted to go a little bit further, you could plug in a 3. 2 to the third would give you 8. So you go ahead and do that as well. That'd be all the way up here. I'm not going to go much further than that because I'm kind of running out of space. But we can see that it seems to be increasing very quickly as it heads off to the right. Or as x approaches positive infinity, you could say. Now what I'm curious about is, while yes, it is certainly quickly increasing to the right and intends to continue doing so, what does it do on the negative side? So since I'm running out of a little bit of space with my XY table, I'm just going to add another one on over here. Let's just plug in negative 1. If we plug in negative 1, that means we are being asked to take 2 to the negative first power. Well, again, this would require a little bit of remembering of your exponent properties, your properties of exponents from the previous lessons. When you're taking something to a negative exponent, what that really means you're doing is dealing with reciprocals, meaning 2 to the negative first is the same thing as the reciprocal of 2 to the positive first. So, when we took 2 to the first, we got 2, right? Which means if 2 to the negative first is what I'm doing, then that should be the reciprocal of our answer. So it'd be 1/2. Positive 1 gave us positive 2. Negative 1 should give us 1/2. So in that scenario then, if I want to plug in negative 2, meaning taking 2 to the negative second power, well, what did 2 to the positive second power give us? Gave us 4. So that should be the reciprocal of 4, should be 1/4. In other words, 2 to the negative second power is equal to 1/2 to the positive second power. And then if we want to do one more just to even things out, then we can plug in negative 3, and so that would give us 1/8, being as positive 3 gave us just 8. So if I graph that, here's roughly negative 1/1/2. Going to have to estimate because we can't use tick marks. 1/4 would be about halfway between the x-axis and the 1/2. And then 1/8 is going to be even closer to the x-axis. And so what we see here is that it almost starts to flatten out. And if you were to graph this on a graphing calculator, you would see that it really would look like it flattens out. Because this is never going to actually hit 0. Right? Think about that for a minute. You can pick any x value you want to plug in, but because this is exponential, it's going to be 2 to the power of that x value. There is no power of 2 that gives you back 0 as an answer. You can plug in the most negative number you can think of, and all it's going to do is give you an extremely tiny fraction. But it will still be a fraction because 2 to any negative power is just taking the reciprocal 1/2 to that power, right? You will never get 0. Moreover, there is no way to take a positive base, a positive b value, and make it negative just from an exponent. You can't do it. If the base started out positive, it will continue to be positive no matter what exponent, no matter what power you take it to. So what we see here is that any exponential function is going to have what we call an asymptote. And we have talked about this in a previous video, so if you haven't watched that video and you're not sure what asymptotes are, you should go back and watch that. More specifically, exponentials, or this exponential, has a horizontal asymptote, right? Meaning it's an invisible horizontal line that the graph does not cross. Asymptotes in general are effectively invisible lines that your function won't cross. This one happens to be a horizontal line. And since it's the y-axis, then that would be the line y equals 0. Now we can generalize that exponential functions are going to have asymptotes. What we can't generalize is that it's y equals 0. That is strictly for this function. There certainly are plenty of other exponential functions that we could make that would have a horizontal asymptote at y equals 0. But not every single one is going to be at y equals 0 because, again, you can always do transformations to change things. But you are going to have an asymptote somewhere for your exponential graph. Okay. Also, just to add to it, the domain and range. Your domain would be that it's going left and right forever. I remember domain is the x's, so if I'm asking about the domain, we're asking how far to the left and how far to the right does the graph go. This one is going left and right forever, so interval notation would be negative infinity to positive infinity, or you could say all real numbers. If we want to talk about the range here, for your range, we already said this graph is not going to go below the x-axis, and in fact isn't even going to touch the x-axis. We can't really pick a specific number for the range to start at, though, because, as we said, it is going off to the left forever, getting slowly smaller and smaller fractions closer and closer to the x-axis. It gets infinitely closer to the x-axis, it just won't ever actually touch it. So what we do is we say that the range starts at 0, but we use a parentheses. Remember, in interval notation, a bracket means it's actually equal to that spot, whereas a parentheses means it's effectively starting right after 0, so 0.000001, right? Except you could continue adding zeros before that one forever. It does head up forever, though, so that would be positive infinity. If you wanted to write your range in inequality notation, you could just say y is greater than 0 and make sure it's specifically greater, not greater than or equal to. But yeah, that's some general information about an exponential graph. The only thing I would add with that is this specific one, being as it is increasing from left to right, we could label this what's called an exponential growth graph, as there are two general kinds. I want to take a look at one more graph. We won't take as long with this one as we did with the other one, but I just wanted to show you the two general kinds of exponentials you could have. So let's say this time I give you 1/2 to the x power. Instead of 2/1 to the x power like last example technically was, we're doing 1/2. Well, again, if we start by plugging in 0, anything to the 0 power is 1. So 1/2 to the 0 power is also 1, just like the last example. Like I said, that'll be reasonably something that you will see a fair amount of times. So if you plug in positive 1, this time 1/2 to the positive first power would be 1/2 itself, the same as 2 to the first was itself, but this time we're getting a fraction. So we'll try and nail it as best we can. That looks like about halfway. If I plug in 2, 1/2 to the second power would be 1/4, meaning we're supposed to get even closer to the x-axis, so on and so forth, right? If I plug in 3, I get 1/8. This time then, let's talk about the negative side, just like we did before. If I plug in -1, well, I'm still supposed to be doing the reciprocal, so if I'm taking 1/2 to the negative first power, the reciprocal of 1/2 is 2/1, so really I'm taking 2/1 to the first power. And we know that 2 to the first is 2. So -1, 2 would be a coordinate point for our graph. If I plug in -2, well, instead of taking 1/2 to the negative second, I'm really taking 2 to the positive second. So that'd be 4. jumping up even higher. And last but not least, if we plug in -3, well, that'd be the reciprocal of what we got for +3. And so if 1/2 to the +3rd was 1/8, then 1/2 to the -3rd should be 8/1, 8. And so what we see here is what almost ends up looking like basically a y-axis reflection of our original exponential graph, where in this case, instead of increasing quickly as it heads to the right, it actually decreases quickly and then flattens out. And so you will notice that it still has a horizontal asymptote at y equals 0, and its domain and range are still exactly the same. It is still going left and right. It may look different, but it is still going to the left forever and to the right forever. And it still, like we just said, does not go any lower than the x-axis, and it does still head up forever. So there's not a huge amount of difference other than just the shape in general. The last one, the last graph we said would be called exponential growth. This we would refer to as an exponential decay graph. If you wanted to really generalize the two different types of exponential graphs you can have, that would be probably the most general way. You can have an exponential growth or an exponential decay.